workshop. So our first speaker is Ján Pich from Charles University in Prague, and will speak about this beautiful topic, about proof complexity of circuit lower bounds.
So we know that patterns that could resolve P are considerably restricted by well-known barriers in computation complexity. And there are several corresponding results in logic stating that certain fragments. There are several corresponding results in logic stating that certain fragments of arithmetic are not sufficiently strong to prove that P differs from NP or similar conjectures. In this talk, I would like to present some of them and discuss possible improvements. To be more specific, I'll speak about Nissan-Wittgerson generators in the context of propositional proof complexity, about feasible disjunction property, and I will venture also intuitionistic logic. Let me start with a short overview. Probably the first significant barrier in computation complexity is relativization by Becker, Gill, and Solovay. It says that there are two different oracles such that in the first relativized world, P equals NP, while in the second relativized world, P is not NP. And Hartmanis gave it a more logical look when he showed that there is an oracle such that the relativized version of P versus NP is independent of ZF. Later, Arora, Impagliazzo, and Vasirani defined a theory called relativized complexity theory, formalizing precisely the relativizing techniques, so their theory cannot solve P versus NP. And Impagliazzo, Cabañez, and Kolokolova did the same thing for algebraization, a stronger version of relativization discovered by Aronson and Wittgerson. But this talk is about proof complexity of circuit lower bounds, and probably the most important barrier for circuit lower bounds is natural proofs by Rasborov and Rudic. Natural proofs can be used to show that the theory of bounded arithmetic called S2 alpha cannot prove superpolynomial circuit lower bounds unless strong pseudo-random generators do not exist. Or in the language of propositional logic, that propositional proof systems admitting so-called feasible interpolation property, like resolution, cannot prove superpolynomial circuit lower bounds efficiently if strong pseudo-random generators exist. Maybe natural proofs can be used to show that the unprovability results for much stronger systems, but the best hardness result of this kind we currently have doesn't use them. It's based on proving hardness of certain Nissan-Wittgerson generators, and it works for res log n, resolution operating with log n DNF formulas.
All the way to res log n? Here below. Does it work to res log n or log log n?
Log n, actually, I think, in your terms. Okay. I would like to define now these Nissan-Wittgerson generators and show how we use them in propositional logic. Also, I will describe more precisely how exactly we formalize the circuit lower bounds and what we mean by the unprovability results I just mentioned. So first of all, there is the notion of proof complexity generator, independently introduced by Aleknovich, Ben-Sasson, Rasborov, and Wittgerson, and by Krajicek. A proof complexity generator is just a function computed by poly-m-size circuits, mapping strings of length n to strings of length m for m bigger than m. But in proof complexity, we are interested in the following propositional formulas expressing the fact that some string b is outside of range of such generator. And this can be encoded in a standard way using variables x1, x2 up to xn for inputs of circuit C computing this generator G, and some additional extension variables y1 up to y poly n for gates of the circuit C. Now, an example of such a generator might take strings of length poly Tn, encoding circuits with n inputs of size Tn, and map them to strings of length 2 to the n, encoding the truth tables of functions computed by these circuits. Then the formula that some string f is not in range of such generator means that the function represented by this string f is not computable by circuits of size Tn. And when we say that it is hard to prove for some function f that is not in P-poly, we mean that for any superpolynomial function Tn, it is hard to prove that this function is not in size Tn. It means that it doesn't have polynomial size proofs in some propositional proof system. So this is the way we formalize circular bounds in propositional logic, and using this formalization, Rasbarov showed that basically all known circular bounds are efficiently provable in extended Frege system. For simplicity, here I have just an illustration of Frege system. This is a well-known Hilbert calculus, and it is considered as a very strong propositional proof system. For us, it's like ZF, and in particular, it would be very nice to show that it cannot prove superpolynomial circular bounds efficiently. In fact, maybe it's impossible to do this.
You mean for us it's like ZF? For us you mean for you or for?
For me. Okay, so the hardness results we have work for much weaker systems, unfortunately, like resolution or its modifications. If you want to derive a tautology in resolution, you need to represent its negation as a set of clauses, means as a set of disjunctions of literals, and then using just this one CAD rule, which allows you to CAD literals, you need to derive empty clause. Here C is a clause and L is a variable or negation of variable. Intuitively, in Frege systems, you are allowed to CAD whole formulas. And in case of res K, you can operate with K DNF formulas and CAD conjunctions of K literals. Now, prominent example of a proof complexity generator is based on a construction by Nissan and Widgerson. Let A be an m times n 0, 1 matrix with L1s per row. So it looks like this. M is bigger than n, and in each row of this matrix you have exactly L1s somewhere at some positions. And for each row I, denote these positions where you have 1s by JIA. And let f be a Boolean function on L variables, then the Nissan-Widgerson generator based on this matrix A and function f will map strings of length n to strings of length m in this way that the ith bit on the input x is just the function f computed on x is restricted to JIA. So for each x, if you want to see the ith bit of this generator, you will just look at the ith row of this matrix. This L elements where you have ones specify some L bits of this input x, and you will compute the function f on this L bits. Now usually it is required that the intersection of JIA and JJA is small. So this is a very nice structure to play with, especially for pure adversary games. And if we set the parameters properly in such NW generator, the hardness of this formulas that some string b is not in range of such generator imply hardness of circular bounds. For example, if you take m as sub-exponential function in n, f a p-poly function, and a suitable combinatorial design, meaning that for any I you can find out efficiently the set JIA, then you can see this generator as it was sending strings of length poly n to strings of length 2 to the n, and moreover, any string in range of such a generator actually represents a function which is efficiently computable, because whenever this happens, that some string b equals nw fx, you can compute this function b efficiently in the following way. The ith bit is just, you'll just find efficiently the set JIA. This can be done because this matrix A has such a nice property, and then you compute function f efficiently again on the proper x restricted to JIA. So this means that all functions in range of such NW generators are efficiently computable, and therefore if it is hard to prove for some function f that it's not in range of such generator, then it is hard to prove that it is not efficiently computable. And Rasbarov showed that if you take f a parity function and A is suitable expander matrix, then this kind of Nissan regression generators are hard for res epsilon log n. And using this, he was able to show that superpolynomial circular bounds are hard for this system, which is not known to admit feasible interpolation property. Interestingly, he even conjectured that these Nissan regression generators should be hard for much stronger systems, like Prague. Assuming that A is a usual combinatorial design, as in the seminal paper by Nissan and Witgerson, here parameters are actually not specified, but take, for example, M might be as big as 2 to the L, where L is the square root of n, and intersection of JA and JJA is always at most log m. Then any Nissan Witgerson generator based on p-poly function, which is hard on average for n-signal circuits, should be hard for Frege. This means that for any string B, it should be hard to prove that it is outside of range of such generator. And analogously, if this Nissan Witgerson generator is based on a function which is in np-poly intersected co-np-poly, or np intersected co-np, hard for p-poly, then it should be hard for extended Frege system. Now, we know that lower bounds for propositional proof systems were often based on or implied circular lower bounds, but here, notice that we are just assuming that some hard function exists, and therefore it's a conditional statement, so it might be easier to prove it. We know that it holds in some form for systems admitting feasible interpolation, and the argument goes like this. If you have in some propositional proof system M P polyemphasized proof of this kind of tautology or formula, then this formula is just a big disjunction of this form. Yeah, here B is a string of length m, so I goes from 1 to m, and here we have disjuncts of this form. So assuming that you have such a short proof in some propositional proof system P of this statement, then feasible interpolation property is such a thing which for any x gives you efficiently in M some I such that BI is not NW fxi. So this just means that the ith bit of B is different from the ith output of this generator, NW. But this is just f computed on xjia, and in fact it turns out that if A is a suitable matrix, then this allows you to compute this function f. So in other words, if the function f is not computable by circuits of size poly n, then this kind of formulas cannot have short polyemphasized proof in any propositional proof system admitting feasible interpolation property. And it's known that systems like resolution or cutting planes admit feasible interpolation, but if you were able to derive, it is known that if you derived feasible interpolation for stronger systems like Frege, you would break RSA. So it seems that the weaker requirement on our proof systems is needed if you want to derive stronger lower bounds. And this could be feasible disjunction property, which I would like to discuss in a moment. First, let me make a more general point. So here we are trying to show that there are hard tautologies for strong proof systems like Frege. But and eventually maybe that NP is not co-NP. But on the other hand, we are also kind of proving that it is consistent with these proof systems, strong proof systems, that they cannot that NP is efficiently computable. We are proving that they cannot refute it efficiently. This is not paradoxical, because if indeed NP is hard for P-poly, then there is a propositional proof system which proves this fact efficiently. So we can say it in this way: if you are able to show this very strong form of consistency, namely that for all propositional proof, it is consistent with all propositional proof systems that NP is in P-poly, then NP is really in P-poly. No, this is fact. Yes.
What is this proposal?
What is this? It's basically you are just firstly checking whether the given input B is SAT. You can do it efficiently in 2 to the n, and then if it is, you accept, otherwise you proceed as Frege, basically. But you don't know whether the system is sound, because if B is not, if SAT is not in P-poly, then if SAT is in P-poly, then this system is not sound. Yeah. So the point is to prove it in some reasonable system like ZF or Frege, which is sound. Otherwise, you have no information about hardness of circular bounds. Okay, so in the beginning I said that proof systems admitting feasible interpolation can't prove superpolynomial circular row bounds unless strong pseudo-random generators do not exist. And this result is based on is using natural proofs. And as I said already, Frege systems it's probably hard to show that Frege systems admit feasible interpolation property. But there is a modification of natural proofs by Drudic, which says the following: that assuming there are so-called superbits, then there is no NP-poly natural proof against P-poly. Here, NP-poly natural proof is any proof such that it implies the existence of a set of Boolean functions C, which is useful, meaning that for any set of sequence of functions from this set C, any sequence of functions from this set C is hard for P-poly. So this is a natural condition. It is large, so for any n number of functions on n inputs in this set C is big. And in fact, it turns out that our lower bounds, circular lower bounds, often work for many functions, not just for one function. And it is NP-poly constructive, meaning that whenever you are given f represented by its truth table, you can decide its membership in the set C using just NP-poly circuits. So this just means that for a lot of functions f, for a lot of hard functions f, you can prove that they are hard efficiently. So the difference between classical P-poly natural proofs against P-poly and NP-poly natural proof is just this constructivity, that here you are allowed to decide the membership in this set C using NP-poly circuits. Now, Rudic needed to assume that there are so-called superbits. These are kind of pseudo-random generators hard for non-deterministic circuits. More precisely, a P-poly function Gn is a superbit if for any non-deterministic circuit of sub-exponential size this inequality holds, which forces the circuit C to find out with a significant success when the given input y is outside the range of such generator G. And it is known that okay, so the assumption that superbits exist is stronger than NP is not co-NP, but still it would be nice to have some explicit hard tautologies for Frege system, just assuming that superbits exist. And in fact, Rudic's theorem implies that if superbits exist, then for any propositional proof system, there are hard functions, hard for P-poly, such that this propositional proof system cannot prove that they are hard efficiently. But this is not good enough for us, because we need f to be something like SAT, or it should be explicitly definable. Now, NP-poly natural proofs can be used to show that assuming superbits there are no propositional proof systems admitting feasible disjunction property proves superpolynomial circular lower bounds efficiently for any function f. And here we say that the propositional proof system admits feasible disjunction property if whenever there is an m-size proof of A or B such that A and B don't share any variables, then there is a poly m-size proof of A or a poly m-size proof of B. So we don't need to find this proof of A or proof of B efficiently. It is sufficient that it exists. And if we oversimplify things, we can say that this is the difference between feasible interpolation property and feasible disjunction property. In feasible interpolation property, you can find this proof efficiently. Here it is sufficient that it exists. Okay, so I think this is a very nice property and it hasn't been investigated very much. For example, I think we don't know any propositional proof system which would admit feasible disjunction property and wouldn't be known to admit some reasonable form of feasible interpolation. But on the other hand, there is also no any negative result like with feasible interpolation, so maybe you don't need to break RSA to show that Frege admits feasible interpolation, feasible disjunction property, sorry. And if you are a constructivist, this reminds you of disjunction property, which is known to hold in many formalizations of intuitionism. For intuitionists, any proof of A or B must be given by proof of A or by proof of B. And I think that naturally it should be given feasibly. So this might look like that in such intuitionistic world, circular lower bounds are not provable unless some hardness assumption fails. But of course it's not so easy. Firstly, positive thing is that Bazan means show that intuitionistic sequent calculus for propositional logic admits feasible disjunction property. And later, Paul would like observe that their proof actually gives feasible interpolation property. Here, intuitionistic sequent calculus is like usual sequent calculus, but there is always at most one formula in the succedent of any sequent. The problem here is that it is not clear how to do this reduction of hardness of circular lower bounds to feasible disjunction property constructively. Okay. I can show you a simple way how this works. Classically, we are trying to prove the following thing. If P proves efficiently that some F is hard, okay, so this is a step in a reduction of circular lower bounds to feasible disjunction property. You are basically doing this that if there is a short proof of hardness of some function, then you can show that for any function g is hard of f plus g is hard. And classically you can do it because you know that if g is actually easy and f plus g is easy, then f plus g is easy, and then then f is easy. And that's contradiction, but this seems to be undoable in intuitionistic logic. Nevertheless, we can still say, as we have feasible interpolation property, we can say that Nissan Gaussian generators are hard for these systems, but this doesn't seem to be so interesting because intuitionistic sequent calculus is not considered as a very strong proof system. It would be much more interesting to show that a theory like intuitionistic S12 cannot prove circular lower bounds, superpolynomial circular lower bounds, encoded as sigma B0 formulas. Here, intuitionistic S12 is axiomatized by a set of basic axioms defining symbols of its language and a polynomial kind of induction for positive sigma b1 formulas. And it has such a nice property that for any x there exists y. If you can prove this kind of statement where a is any kind of formula, then there is a polynomial time function which gives you witnesses for these y's efficiently. And so this might be considered as a formalization of feasible constructive mathematics. And Jeremy Avigad showed that S12 theory, a classical counterpart of intuitionistic S12, is for all sigma b1 conservative over intuitionistic S12 theory. And this means that if circular bounds are unprovable in intuitionistic S12, then they are unprovable in S12. So, and S12 corresponds to extended Frege system, so it's very strong theory, and it means that it is probably hard to show that intuitionistic S12 theory can't prove circular bounds, but still it makes sense to study feasible disjunction property in this context. And Bas and Mintz show that in general it doesn't hold in predicate logic, because they constructed a sequence of disjunctions with short proofs in intuitionistic predicate logic, such that there are no polynomial size proof of disjuncts. But for us, it would be actually sufficient. It is actually sufficient to have the following kind of feasible disjunction property: that whenever you can prove for all x, ax, or bx, where a and b are pi b1 formulas, then for each x there is a short proof of ax or a short proof of bx. And this seems to hold in intuitionistic S12 theory. But again, it doesn't give us any unproved. It doesn't say that that circular bounds are not provable in S12, because despite this conservativity result, it seems that this step, this non-constructive step, seems to be undoable. But yeah, who knows? Maybe there is a way how to manage this somehow. I think that I'll stop here. Thank you very much for your attention.
So we have time for questions. Any questions? Okay. Thank you very much.